In this last part, we will present the unified and general map T, P, Q that encompasses the classical Collatz map C, together with the map T. The answer to the three questions is formulated by Mohammadi as a general conjecture. To understand the heart of this research, we must look at the parameters that define this new landscape. The author introduces two positive integers, P and Q, where P is always greater than or equal to Q. From these two values, the entire system emerges. The divisor, D, is the sum of 2 to the power of P and 2 to the power of Q. The coefficients, alpha and beta, are then derived from this same logic, ensuring a perfect modular balance. This defines the mapping T, P, Q, where for any integer n, the result is always an integer. If n is a multiple of D, the map simply performs a division, reducing the value's magnitude. But when n is not divisible by D, the mapping applies a specific linear growth. The formula, alpha times n, plus beta times the rest in the division of n by D, all divided by D, ensures that the output is always an integer. We use the notation, bracket n sub D, to represent the remainder of the Euclidean division of n by D. The definition of the map T, P, Q is a crucial property. It preserves the integrity of the discrete dynamical system. By tuning the parameters P and Q, the author has transformed a single numerical path into a structured family of trajectories. In this framework, the original Collatz conjecture is merely the starting point, where P and Q are both 0. And if we set P to 3 and Q to 1, we obtain the modulo 10 system we just explored. By expanding to any P and Q, we discover a vast landscape of discrete dynamical systems. Through this generalization, we could potentially gain a deeper understanding of the conjecture's underlying structure. By stepping beyond the narrow path of the original problem, we may perhaps see the hidden architecture that governs these numbers, the power sum divisor, the multiplier, and the increment. Mathematics often reveals its deepest secrets through the lens of generalization. As the mathematician Richard Courant said, the map T, PQ may be written as given here. We can simplify the definition of T, PQ as given in this formula. We can observe that if the difference P minus Q is a power of 2, such as 2 to the power of r, for some integer r, then the divisor integer may be seen as a Fermat number. We have the boxed formula written in blue. The detailed proof of this formula may be found in the paper of Mohammadi. Large omega of small omega is a notation for a cycle starting from an integer small omega. The trivial cycle is given by its starting integer, together with its length. As a consequence, for all positive integers P and Q, such that P is greater than or equal to Q, the map T, P, Q, has at least the trivial cycle, starting from 2 to the power of P minus Q. As you can see, the trivial cycle is explicitly given here. Now, you can see some examples of the trivial cycle for different values of the parameters P and Q. The unified conjecture may be formulated as follows. For all positive integers P and Q such that P is greater than or equal to Q. First, if the couple P, Q, does not belong to the exceptional set E, then the map T, P, Q, has exactly the trivial cycle as the unique cycle. Second, if the couple P, Q belongs to the exceptional set E and is different from the couple 5, 2, then the map T, P, Q has exactly two cycles, the trivial cycle and also a secondary cycle starting from the integer omega sub P, Q. And finally, the map T, 5, 2 has exactly three cycles, the trivial cycle and also two other secondary cycles. All the trajectories are bounded and eventually reach an element of the attractor set A, P, Q. The attractor set A, P, Q and the exceptional set E are given explicitly by the written formula. As you can see, all the elements omega, P, Q are given in the table you are seeing on the screen. As you will see, all the secondary cycles are explicitly known. At the end of this video, I will show you a Python code and also a simulator, in which all the secondary cycles are explicitly given. Just for illustration, we show you some examples of trajectories for different values of the couple P, Q. Now, to give some numerical analysis of the basin attractor when we have a secondary cycle. We may ask this question: which cycle attracts more integers? We give the answer as a percentage for the starting integers up to 10 million. For different cases, we have the percentage of the basin attractor. As we can see, the trivial cycle attracts a higher percentage of elements, except for the case P equals 1 and Q equals 0, where the secondary cycle attracts a larger percentage of integers. The unified conjecture was tested by computer until Pmax equals 20, for all integers n up to 10 to the 9th power. This is about more than 200 billion trajectories. Let us now show you some curves representing the trajectories for different values of P and Q. We observe that the trajectories always reach the basin, according to the unified conjecture. You can also see many different graphs representing the process for some different values of the parameters P and Q. As you can observe, for a couple P, Q, belonging to the exceptional set E, we have secondary cycle, so the graph of such corresponding process is not connected, and the process is represented by two graphs or three graphs in the case of the couple 5, 2. As in the previous part, let us now examine a simple Python script. We will write this code to compute the trajectory of a given integer n for different values of the parameters p and q. This script will be slightly different from the previous one, though we follow the same directives. First, we define the nextTerm function. As its name suggests, this function computes the next term for an input integer n. The function is coded to strictly follow the mathematical definition of the map T, P, Q. Then, we define the trajectory function. This generates the trajectory as a list, starting from an input number n, and stopping only when it reaches an element in the attractor set A, P, Q. In the code, this set is simply defined as A. Next, we define the exceptional set, E, as a dictionary, according to the table previously shown on the screen. From this set E, if the tuple P, Q is found within it, the code automatically updates the attractor set. As in the previous code, we use a while loop to continue the calculations until our variable m belongs to the attractor set A. Each step is stored in a list called traj. Note that in this trajectory function, there is no limit on the number of iterations. If the trajectory of an initial integer were to never reach the attractor, the while loop would run infinitely. After that, we use print statements to output the resulting list of trajectories for our starting number. As you can see, we have tested the code using both small and large numbers for different tuples P, Q, and notice that, for all our tests, the sequence eventually reaches the attractor set A. For a very large number, the trajectory may be quite long, reaching the attractor after more than 1,000 steps, or perhaps even more. Finally, we generate graphs to visually illustrate these trajectories. Just like with the previous code, I encourage you to pause the video, copy this code, and experiment. What happens if you try a number with 100 digits? Feel free to experiment and improve the code using your own imagination. To help you visualize these dynamical systems, a dedicated online simulator is available on GitHub pages. Let us see how it works. First, you choose your parameters P and Q. For example, if you input 3 and 1, you will recover our famous rule of 10. As soon as you set these parameters, the simulator automatically generates the specific conjecture statement. It tells you the exact number of expected cycles and displays their values. Next, you enter your starting number n and click on Simulate Trajectory and Draw Graph. The tool instantly calculates the steps and renders an interactive visualization of the sequence. You can zoom in on the graph and even export it as a PNG or SVG image. Please note that this educational tool is not optimized for extremely large numbers. I invite you to explore this mathematical universe on your own. You will find the link to the simulator in the description below. As a conclusion, the unified conjecture introduced by Bohamidi has been explained in detail, with many examples, animated trajectories, and illustrations. First, we explained how the map T, P, Q works. After that, we exposed the main unified conjecture, and we explained the attractor set, together with the exceptional set, E. Many challenging questions arise from this study. Challenge 1. The quest for order 4. Is it possible to find a pair, P, Q, with 4 or more distinct cycles? Challenge 2. Is it possible to find a secondary cycle, with a length of more than 630 steps? Challenges 1 and 2 may be said in other words, is the exceptional set, E, complete? The ultimate challenge remains. Prove, or disprove, the general unified conjecture. You can also code this unified conjecture, and explore it by computer. Maybe, you will be the one who disproves it. I hope that you enjoyed this presentation. Please, let me read your comments and remarks on this work introduced by Bohamidi. Thank you very much for your attention.